Welcome to this video on powder bed fusion, specifically focused on polymer selective laser sintering, or SLS. We will explore the physics, thermal management, parameter mapping, and material reusability in this process. In this first part, we will introduce the core mechanics and physics that enable selective laser sintering. Selective laser sintering, or SLS, is a key additive manufacturing technology within the powder bed fusion category. It uses a focused laser to selectively fuse layers of thermoplastic polymer powder, with the surrounding unfused powder providing support. The process relies on two core principles. First, powder deposition, where a thin, uniform layer of polymer powder is spread across the build platform. Second, layer-wise fusion, where the laser scans the surface to fuse particles together. The laser serves as a precise heat source. When photons strike the polymer surface, they are absorbed and converted into thermal energy, which creates the melt pool required for structural integrity. Several factors define powder bed dynamics. The particle size distribution affects flowability, morphology influences packing, and thermal conductivity of the unsintered bed helps retain heat and reduce warping. Thermodynamics are critical in SLS. The process operates near the melting temperature of the polymer, with the laser providing the localized energy to cross the phase boundary and create a viscous melt. Unlike some other processes, polymer SLS often utilizes a partial melting mechanism known as core shell fusion. Here, the particle surface melts while the core remains solid, which aids in maintaining part geometry. The choice of material is essential. Semi-crystalline polymers like Pa12 offer a sharp melting point and are common in SLS, whereas amorphous polymers like PC require precise temperature management. A successful build depends on the sintering window, which exists between the crystallization temperature and the melting temperature of the polymer, ensuring the material remains in the ideal state for fusion. Moving on to part 2, we will look at the physics of sintering, focusing specifically on neck formation and consolidation. Neck formation is the earliest stage of coalescence. As the laser hits the powder, surface tension drives the molten surfaces to merge, forming a neck that directly impacts the part's final strength. The Frenkel-Eshelby model mathematically describes the rate of this neck growth, assuming Newtonian viscous flow in the initial stages of the sintering process. Two key forces are at play: surface tension, which acts as the driving force for consolidation, and zero shear viscosity, which acts as the resisting force that needs to be overcome by laser energy. Ultimately, the coalescence rate decreases as viscosity increases. This means high-performance polymers, such as PEEK, require significantly more thermal energy to overcome viscous resistance compared to lower viscosity materials. Moving beyond initial neck formation, full consolidation requires complete void elimination. The melt pool must remain fluid long enough for trapped gases to escape. Otherwise, the melt freezes prematurely, leaving defects. This process happens in stages. Initial contact leads to high porosity, followed by rapid neck growth as pores close, and finally, gas diffusion ensures full densification of the melt track. Beam-matter interaction is crucial. When the CO2 laser strikes the rough powder surface, particles scatter and absorb the radiation. Penetration depth is determined by the polymer's optical absorption coefficient. We must manage optical penetration carefully. The laser must penetrate deep enough to ensure interlayer adhesion, but over-penetration can cause overheating and degradation, leading to a loss of dimensional accuracy. We also have to consider the heat-affected zone. This includes the high-temperature melt pool, the boundary zone where particles partially fuse, and the surrounding powder bed, which provides support and thermal insulation. In part 3, we explore thermal management, which is essential for maintaining the environment and ensuring optimal part quality throughout the build. Powder preheating is a fundamental step. By heating the bed just below the melting point, we minimize the energy needed from the laser and drastically reduce thermal gradients, which helps prevent warping. Operating near the melting point is a balancing act. If the temperature is too low, parts curl. If it is too high, the entire bed fuses into a solid cake, ruining the build. Maintaining a shallow thermal gradient is key. It ensures that internal stresses don't pull the geometry out of shape during the delicate melting phase. The chamber is flooded with nitrogen to prevent oxidation. At such high temperatures, even small amounts of oxygen would cause rapid degradation, ruining both the part and the powder's reusability. Without nitrogen, the powder degrades and becomes brittle. With nitrogen, we preserve the polymer, allowing a significant percentage of unused powder to be safely blended and reused. Cooling is just as critical as heating. A slow, controlled cooldown allows the polymer chains to fold into dense, strong crystalline structures, while rapid cooling leads to thermal shock and warping. This management ensures the proper balance of crystalline and amorphous domains. Proper cooling prevents the polymer from being locked into a weak, amorphous state. The post-build cooldown follows a precise timeline, from the initial heat-off phase, through natural convective cooling, until the geometry is finally locked and the chamber is ready to be opened. Finally, Remember that the build chamber has distinct zones. The top surface, core part bed, and feed pistons each experience different thermal demands that the machine must balance to ensure a successful print. We are now moving into Part 4, where we explore the parameter maps that allow engineers to precisely control the SLS process through laser power, scan speed, and energy density. SLS part quality relies on the delicate balance of 4 primary parameters: laser power, scan speed, hatch spacing, and layer thickness. These variables collectively determine the energy delivered to the powder. Laser power, measured in watts, is our primary heat source. Higher power increases the depth of the melt pool, but finding the right balance is crucial. Too low, and particles won't fuse. Too high, and you risk polymer degradation. Scan speed dictates how long the laser dwells on any single point. It must be balanced with power. Faster speeds are better for productivity, but they reduce the time available for heat conduction, which can lead to incomplete fusion. Hatch spacing determines the overlap between laser passes. Insufficient overlap leaves voids, while too much causes heat buildup. Layer thickness determines your resolution, where thicker layers require more energy to ensure proper fusion through the entire depth. These parameters are deeply interdependent. A change in one, such as scan speed, necessitates a proportional adjustment in power or spacing to maintain the integrity of the part. To simplify this complexity, engineers use a unified metric called the Andrew number, or energy density. This provides a way to calculate the total energy applied to a given area or volume of powder. The area energy density equation balances laser power against velocity and hatch spacing. When volume is considered, we also divide by the layer thickness, providing a measurement in joules per square millimeter. While energy density is a useful metric, keep in mind that the same value can be achieved with different combinations of parameters. Different paths lead to different thermal histories, which can change the final mechanical properties of your part. Researchers create parameter maps to identify the optimal processing window. This is a stable region where parts achieve high density without degradation, bordered by risks like material vaporization at the top and balling effects at the bottom. This brings us to Part 5, where we discuss powder reusability and the mechanisms that cause degradation over time during the build process. Degradation generally occurs through 2 mechanisms: chain scission, where heat breaks polymer chains, causing embrittlement, and cross-linking, where chains bond together, significantly increasing melt viscosity and hindering future sintering. The orange peel effect is a common defect caused by using highly aged powder. Because the viscosity has increased, the melt pool fails to flow correctly, creating a rough surface and reducing the tensile strength of the finished part. Because powder degradation varies by location in the build chamber, Z-axis performance can suffer. If older powder is used, the melt pool may become too shallow to properly bond with the previous layer, leading to delamination. To manage this, operators use a refresh rate. By blending a specific percentage of fresh virgin powder with used material for every build, they maintain consistent melt viscosity and extend the usable life of the powder supply.